In 1974, two American astronomers pointed a radio interferometer at the center of the Milky Way and found something they were not entirely sure how to describe: a compact, unusually bright radio source sitting at the very heart of the galaxy. They were cautious in their paper. They did not call it a black hole. The word was, at the time, almost too controversial to use in a serious scientific publication. Instead, they described it as a physical structure that defines the galactic center. 8 years later, one of them gave it a name. He called it Sagittarius A. The asterisk was deliberate. In atomic physics, an asterisk after a symbol indicates an excited state, something that is not at rest, that is doing something energetic. He chose it because he thought the source was interesting. He had no idea, at the time, just how interesting. Northwestern University, late evening, 2024. The office of Farhad Yusef-Zadeh, astronomer. 40 years studying the center of our galaxy. He has spent more of his life thinking about Sagittarius A than most people have spent thinking about anything at all. Tonight, he is alone with new data. His team has been awarded a rare allocation of observing time on the James Webb Space Telescope. 48 hours total, spread across an entire year, divided into long observation windows, 8 to 10 hours each, pointed at the same single target, the supermassive black hole at the center of the Milky Way galaxy. The first batch of data has just come down. He opens it on his monitor. What he sees should not be there. The brightness of Sagittarius A over time, recorded in 2 different infrared wavelengths, is not steady. It is not even merely flickering, the way the textbook says it should. It is erupting. Bright, sustained flares, lasting hours, faint, fast pulses, lasting seconds, patterns of variability that do not match what was predicted. Patterns of variability, in fact, that do not match what anyone predicted. He scrolls to the next observation window, different data, same kind of behavior. The next observation, taken weeks later, different again, but again, never quiet. He keeps scrolling. Across 48 hours of total observing time, spread across an entire year, sampled in different seasons, with different instrument settings, the closest supermassive black hole to Earth has not, even once, gone into the calm, low-activity state that low-luminosity black holes are supposed to spend most of their time in. Not for an hour, not for a few minutes, not at all. Yusef-Zadeh writes a sentence in his notes that, by early 2025, will appear in a peer-reviewed paper in the astrophysical journal Letters. The sentence becomes the line that captures everything the team has seen. We saw something different each time. Nothing ever stayed the same. He underlines the second sentence, because what the data is telling him, repeatedly, across an entire year of observation, is something the field has not been ready to hear. The textbook says supermassive black holes in low-luminosity galaxies, black holes like ours, are supposed to be quiet, dormant, slowly feeding on small amounts of gas and dust, producing occasional flares, separated by long periods of calm. That is the picture every introductory astronomy course teaches. That is the picture every analytical model is built around. Sagittarius A is doing the opposite. It is, in his own words, always bubbling with activity, and it never seems to reach a steady state. The closest supermassive black hole to Earth was supposed to be sleeping. It isn't, and the more carefully astronomers watch it, the more they realize they don't yet know why. Yusef-Zadeh is not an outsider in this field. He is not a contrarian. He is not someone who chases anomalies for the sake of being interesting. He has been studying the galactic center for over 40 years, and he is among the most respected voices in the discipline. He had models in mind for what Sagittarius A should look like during the Webb observations. The data refused them all. So, he proposed something else, that none of our existing analytical models are quite right. This video is about Sagittarius A. It is the supermassive black hole at the center of our own galaxy, approximately 4 million times the mass of the Sun, packed into a region of space smaller than the orbit of Mercury, sitting roughly 26,000 light-years from Earth. It is invisible. By definition, black holes do not emit light. But its effects on the matter around it can be observed in radio waves, infrared light, and X-rays. And, by studying those effects, astronomers have built up, over the last 50 years, a detailed picture of what this object is. It is the closest supermassive black hole to us, by a factor of more than 100. Every other supermassive black hole we have studied is in another galaxy, millions, sometimes billions, of light-years away. Sagittarius A is in our own galactic neighborhood. We can watch it on timescales of hours and days, rather than years and decades. We can study it with a precision that is impossible for any other object in its category. It was first imaged directly by the Event Horizon Telescope in 2022, an iconic orange ring, with a dark central shadow, that became one of the most famous scientific images of the decade. It was imaged again, in polarized light, in 2024, revealing strong, organized, spiraling magnetic fields, and hinting at the existence of a jet that we have not yet directly detected. And it was observed by the James Webb Space Telescope across 7 windows in 2023 and 24. Observations published by Yusef-Zadeh and colleagues in February of 2025, revealing behavior that does not match any prior assumption about how a supermassive black hole of this type should act. This is not just about a black hole. This is about the one supermassive black hole we can actually watch in real time, close enough to study its behavior across hours rather than years, close enough that the most powerful telescopes ever built can resolve its environment with sufficient detail to ask questions that no other black hole in the universe will let us ask. And what that black hole has been telling us in the last few years is something the textbooks were not prepared for. By the end of this video, you will understand exactly what Sagittarius A is doing that astronomers did not expect. You will understand why it matters beyond our own galaxy, why the closest black hole to Earth has just become one of the most important laboratories in modern physics. And you will understand why the simple picture we built of supermassive black holes, the picture that has been in textbooks for decades, may be quietly coming apart at exactly the moment we have finally developed the instruments to look closely. So, what is actually happening at the center of our galaxy? Why does Sagittarius A never stop flaring when every theory said it should be quiet? Why are the magnetic fields around it organized into a spiraling structure that may be hiding a jet we have never directly detected? What does it mean that, in 2025, astronomers used the most powerful telescope ever built to watch this black hole and saw something different in every single observation? Why are some researchers now openly saying that our analytical models of supermassive black hole behavior may have to be rebuilt? And what does any of this tell us, if it tells us anything at all, about the trillions of other supermassive black holes scattered throughout the universe? Black holes we cannot watch this closely, and whose behavior we have inferred from imperfect observations of objects much further away. This is not a video about a black hole eating Earth. It is not about Sagittarius A threatening our planet, our solar system, or our galaxy in any direct way. The black hole is 26,000 light-years away. Whatever it is doing safely, far from us. Anyone telling you otherwise is selling something, usually fear, usually for clicks. That is not what we are doing here. This is a video about science, about the closest supermassive black hole to Earth, doing something that the people who have spent their careers studying it did not expect to see. About observations from the most powerful telescope ever built that have, in the last 2 years, quietly upended assumptions that the field has held for decades. About a roughly 4 million solar mass object at the heart of our galaxy that has refused to be the calm, dormant feature of the Milky Way that it was supposed to be. Stay with me, because, by the end of this, you will understand something about black holes, and about the limits of our current models, that almost nobody talks about, but that is hiding in plain sight in the technical literature. Before we go deeper into the data, if these are the kinds of stories that pull you in, real frontier science explained carefully and honestly, hit subscribe. Galaxy Pulse goes beyond the headlines. Every single time, we will not waste your attention. We will not dramatize what does not need dramatization. The truth, when told properly, is more interesting than the clickbait version. Now, back to Sagittarius A, and the long, strange story of how we even came to know it was there. To understand why a supermassive black hole at the center of our galaxy is acting in ways that surprise the people who study it, we have to first understand how we even know it exists. We have never seen the black hole directly. Black holes are, by definition, invisible. We have inferred its existence, measured its mass, and ultimately imaged its silhouette. Through decades of patient work that began with a small radio source nobody quite understood, and ended with one of the most famous photographs in scientific history. That story begins, surprisingly enough, in the early 1970s. The center of the Milky Way galaxy is not, despite what science fiction would suggest, a clean and tidy place. It is one of the densest, most chaotic, most cluttered regions of space anywhere in our cosmic neighborhood. Millions of stars are packed into a volume that, by galactic standards, is tiny. Clouds of interstellar gas and dust drift through the region in complex, turbulent patterns. Massive stellar explosions have left behind remnants that still glow in X-rays. The gravitational pull of the central mass distorts the orbits of nearby stars, sending them on tight, looping paths around an invisible object at the very center. For most of the 20th century, astronomers could not see any of this directly. The reason was simple and frustrating. Between Earth and the galactic center sit thick clouds of interstellar dust. That dust absorbs visible light almost completely. If you point an optical telescope toward the center of the Milky Way, you do not see millions of stars. You see a wall of dark, obscuring gas. The galactic center, in optical wavelengths, is one of the most opaque regions of the sky. The breakthrough came with radio astronomy. Radio waves pass through interstellar dust, the way visible light does not. Beginning in the 1950s and accelerating through the 60s and 70s, radio telescopes began to map the galactic center for the first time. What they found was complex. There were bright, extended structures, glowing supernova remnants, swirling clouds of ionized gas, and thread-like filaments running across the region. In February of 1974, 2 American astronomers, Bruce Balick and Robert Brown, working with the National Radio Astronomy Observatory's interferometer in Green Bank, West Virginia, noticed something specific within all this complexity. There was an unusually compact, unusually bright radio source at the very center of the galactic center. It was small, it was steady, and it was bright enough that it stood out against the chaotic background. They published their finding. They described it, cautiously, as a physical structure that defines the galactic center. They did not call it a black hole. The word was too controversial at the time for a young scientist to stake a career on. 8 years later, Brown gave the object its name. He called it Sagittarius A. The asterisk was chosen deliberately. In atomic physics, an asterisk after a symbol indicates an excited state, something doing something energetic. Brown felt the source deserved the notation. He felt that it was something interesting. For decades after the discovery, what Sagittarius A actually was remained an open question. It was bright, it was compact, it was at the center of something. But what kind of object could produce such a steady, focused radio signal in such a small volume of space? The candidates included a dense cluster of stars, a small black hole, a neutron star, or something genuinely exotic. The case for a supermassive black hole was built slowly through the 1990s and the first decade of the 21st century. Two teams in particular, working independently on opposite sides of the world, drove the answer. One team was led by Reinhard Genzel in Germany, working with the Very Large Telescope in Chile. The other was led by Andrea Ghez at UCLA, working primarily with the Keck Observatory in Hawaii. Both teams used the same technique. They did not try to image Sagittarius A directly. They watched the stars near it. By tracking individual stars, observation by observation, year by year, they could trace the orbits those stars were moving on, and the orbits told the story. The stars were moving fast. They were on tight, elliptical paths around an invisible point in space, a point that had to contain enormous mass, packed into an extraordinarily small region. Pause here for a moment, because this part is genuinely remarkable. There is a star called S2, also catalogued as S02, which orbits Sagittarius A on a path that takes it within just 17 light hours of the black hole at its closest approach. Its orbital period is approximately 16 years. At its fastest point, S2 is moving at over 7,000 kilometers per second, roughly 2 to 3% of the speed of light. We have now watched S2 complete more than one full orbit since precise tracking began. The shape of that orbit, traced point by point across more than a quarter century of observation, is one of the most direct pieces of evidence we have for the existence of a supermassive black hole anywhere in the universe. Genzel and Ghez shared the 2020 Nobel Prize in Physics for this work. By the time the Nobel was awarded, the existence of Sagittarius A as a supermassive black hole was no longer in dispute. The question had moved on. The new question was simpler and stranger. Now that we know it is a black hole, what is it doing? Under standard models of supermassive black holes, here is what we should have expected from Sagittarius A once we could observe it carefully. A relatively quiet, low-luminosity object, feeding slowly on small amounts of gas and dust drifting in from the surrounding region, producing occasional flickers, perhaps a flare every few days or weeks when a particularly large clump of material happened to fall in, but mostly quiet. This was not a guess. The classification of Sagittarius A in the technical literature is low-luminosity AGN, or low-luminosity active galactic nucleus. The whole point of that category is that the object emits relatively little energy compared to the more dramatic supermassive black holes in other galaxies. The bright quasars we see at the centers of distant galaxies, objects that outshine entire galaxies, are at one end of the supermassive black hole spectrum. Sagittarius A was supposed to be at the other end, quiet, slow-feeding, dim. That was the textbook picture going into the modern era of observation. What Sagittarius A turned out to be, when we finally got the instruments to look closely, was something different, not dormant, not quiet, always doing something. And the closer we looked, the more something there was. The category of low luminosity AGN, as the textbooks defined it, was not built around objects like what SGR-A turned out to be. The flaring rate was wrong. The variability patterns were wrong. The quiet periods, when they appeared, were not as quiet as they were supposed to be. There were two possible interpretations. Either Sagittarius A was unusually active for its kind, an outlier in its category, a specific object with specific conditions that made it more energetic than its peers, Or, and this was the more uncomfortable possibility, its entire category was wrong. Other low-luminosity, supermassive black holes throughout the universe might be similarly active. We just had not yet been able to watch them carefully enough to notice. Either possibility had implications for our understanding of black holes throughout the cosmos. The closest object in any category is the one we should study most carefully. Because what we learn from it, we extrapolate to objects we cannot study as well. If our model of Sagittarius A needed updating, our model of every other low-luminosity, supermassive black hole across the entire observable universe might need updating too. The first signs that Sagittarius A was more active than expected did not come from a single dramatic discovery. They came from a slow accumulation of small observations across multiple wavelengths that began in the early 2000s and built up over the next 2 decades. The earliest detections came from the Chandra X-ray Observatory. Chandra is a NASA telescope launched in 1999, designed to observe the universe in X-ray light. X-rays come from extraordinarily hot or energetic processes. The regions immediately around black holes, wherein falling matter is heated to millions of degrees. Chandra was designed, in part, to look closely at objects like Sagittarius A. Beginning in the early 2000s, Chandra began detecting brief, bright X-ray flares from the direction of Sagittarius A. The flares lasted minutes to hours. They were not constant. They appeared, brightened, and then faded back into the background. By themselves, these flares were not unprecedented. Black holes flare. The presence of flaring activity at Sagittarius A was, in fact, expected. The question was the frequency. Independent observations, primarily from large ground-based telescopes equipped with adaptive optics. The Keck Observatory in Hawaii, the Very Large Telescope in Chile, began detecting similar flaring activity in near-infrared light. Different wavelengths, sometimes correlated, sometimes not, but the same general picture. Sagittarius A was not a steady source, it was a variable one. The early interpretation was straightforward. Occasional accretion events. A clump of gas falls in toward the black hole. As it spirals down through the accretion flow, it heats up to millions of degrees, releases a burst of radiation, and produces a flare. The flare fades. The system returns to baseline. Wait some weeks or months, repeat. This was the standard story. It fit, more or less, what the data was showing in the first decade of the new millennium. The problem was that as observations got longer, more detailed, and more multi-wavelength, the standard story stopped quite working. By the late 2010s, multi-wavelength observations began revealing flares occurring on much shorter timescales than the simple accretion model predicted. Flares lasting just minutes, sequences of flares occurring close together in time. Patterns of brightness, changes across radio, infrared, and X-ray wavelengths that did not match the simple explanation. In 2018, a peer-reviewed paper from a team led by Giovanni Fazio at the Harvard-Smithsonian Center for Astrophysics described flare events in detail. The team had observed Sagittarius A simultaneously in submillimeter wavelengths, X-rays, and near-infrared. What they found was a sequence of brightness increases across these very different wavelengths, all happening within roughly an hour of each other. The paper noted that these events appeared to upend assumptions that have been the basis of some analytic models of flaring in Sagittarius A. That phrasing matters. Appeared to upend. Not definitively overturned. The authors were being scientifically careful. The events could, in principle, have been coincidences, but the paper made the point that needed to be made. The data was no longer fitting the simple models. More observations were needed. More observations came, and the pattern did not fade. Before we go further, let us slow down for a moment and make sure the science here is clear. Because the rest of this story depends on understanding a few things, and they are not difficult. They have just been buried, in most popular coverage, under either too much technical jargon or too much speculation. The first question, what is an accretion disk, and what does it have to do with flares? A black hole, on its own, does not emit light. It cannot. By definition, anything that crosses its event horizon, the surface from which not even light can escape, is gone. We cannot see the black hole itself. What we can see is what happens to matter as it falls toward the black hole. When gas, dust, or other material drifts close enough to a black hole to be captured by its gravity, it does not fall straight in. It spirals, the same way water swirls around a drain rather than dropping straight through. As the material spirals, it speeds up. Friction within the swirling disk heats it to extraordinary temperatures, millions of degrees in some places. At those temperatures, matter glows brightly across a range of wavelengths. Radio, infrared, X-rays. That swirling, glowing structure is called the accretion disk. It is what we actually observe when we observe a black hole. We are not seeing the black hole. We are seeing the bright halo of matter just outside it, before it crosses the point of no return. Flares happen when the accretion disk does something dramatic. A magnetic field line gets twisted past its breaking point and snaps. A clump of denser material falls in and disrupts the flow. Turbulence in the plasma releases a burst of energy. These events produce the bright pulses we observe. The second question, why was Sagittarius A expected to be quiet? Because it has a low feeding rate. Compared to the more dramatic supermassive black holes at the centers of distant galaxies, which are surrounded by abundant gas being actively pulled in. Sagittarius A is a slow eater. There is not much material falling in at any given moment. With less material, there should be less heating, less brightness, and fewer flares. That was the textbook prediction. The third question, what is active? In the sense astronomers use the term, active does not mean dangerous. It does not mean approaching some kind of explosive event. It means the source is producing variable brightness across multiple wavelengths, on multiple timescales, in patterns that do not settle into a simple steady state. Sagittarius A is active in this technical sense. It is constantly producing observable variability. It is doing something, energetically, all the time. What that something is, exactly, is the question that the most recent observations have made urgent. So here is where the stakes start to rise. If the JWST observations are correct, and at this point, we are talking about findings published in peer-reviewed journals by experienced researchers, confirmed across multiple wavelengths and multiple observing windows, then Sagittarius A is not a typical low-luminosity, supermassive black hole. And if Sagittarius A is not typical, then either we have to revise our category of low-luminosity black hole, or we have to acknowledge that this particular black hole is doing something the textbook has not yet figured out how to describe. Both possibilities matter. Here is why. Sagittarius A is the closest supermassive black hole to Earth by a factor of more than 100. It is the only object in its category that we can observe at this level of detail. Every other supermassive black hole we study is in another galaxy, vastly more distant, observable only at lower resolutions and on longer timescales. Whatever we learn about Sagittarius A directly informs our understanding of every other supermassive black hole in the observable universe. If our model of SGR-A is wrong, our models of distant supermassive black holes, which we cannot watch as carefully, may also be wrong, in ways we have not yet diagnosed. There is also a broader consequence. Black holes, despite being individual objects, have outsized effects on the galaxies around them. The energy and material they release, through flares, jets, outbursts, and winds, shape the surrounding interstellar medium across thousands of light years. They influence where stars can form. They affect the chemistry of galactic gas. They drive feedback processes that, on long timescales, regulate how galaxies evolve. If supermassive black holes are more active than current models account for, the implications cascade outward. Galaxy formation models, star formation rate predictions, the energy budget of entire galactic systems. All of these depend, ultimately, on what black holes are doing. So, when Sagittarius A refuses to behave the way the textbook says it should, the question is not just academic. It is a question about how well we understand the engines that shape galaxies. If the first detections of unusual activity had been the only puzzle, the story might have settled into a footnote. Astronomers would have adjusted their models. The textbooks would have gotten a new paragraph, and Sagittarius A would have returned to being one of many studied objects. That is not what happened, because, in 2022, the entire scientific picture of this object changed in a single moment. When the Event Horizon Telescope released the image that nobody had thought we would actually see, at least not in our lifetimes. The Event Horizon Telescope is not a single telescope. It is a global array of radio observatories, scattered across multiple continents, operating together as a single virtual instrument. At the time of the key observations, the array involved 8 separate telescopes in Chile, Mexico, the United States, Spain, France, Greenland, and at the South Pole. By combining the signals from all of these instruments, using a technique called very long baseline interferometry, the EHT achieves an effective resolution roughly equivalent to being able to read the fine print on a document from thousands of kilometers away. That resolution is what made imaging Sagittarius A possible. The EHT first conducted a coordinated observing campaign in 2017. The campaign targeted 2 black holes simultaneously. One was M87*, the supermassive black hole at the center of the galaxy M87, in the Virgo cluster, 53 million light-years away, but 6.5 billion solar masses. The other was Sagittarius A, at the center of our own galaxy. The M87* image was released first in 2019. It became, immediately, one of the most famous scientific images in history, the first direct picture of a black hole's silhouette ever produced. The Sagittarius A image took 3 more years. The reason for the delay was technical, and it matters for understanding what came later. M87* is a much larger black hole than Sagittarius A. Larger black holes vary on longer timescales. Their accretion disks complete an orbit in days or weeks, rather than minutes. During the hours of an EHT observing window, M87* essentially holds still. It looks like a static object. The interferometric techniques used to combine signals from multiple telescopes work cleanly, because the source itself is not changing during the observation. Sagittarius A is far less massive than M87*. Its accretion disk completes a full orbit in just minutes. During an EHT observing window of several hours, the source changes substantially. The matter around the black hole is moving. The brightness pattern is shifting. Standard interferometric imaging methods, designed for static sources, do not work. The EHT team had to develop entirely new imaging algorithms, specifically for Sagittarius A. They had to figure out how to take a series of changing snapshots, each one slightly different from the last, and combine them into a single coherent image that captured what the black hole's silhouette typically looked like. The work took years. The image was finally released in May of 2022. What it showed was extraordinary, and at the same time, deeply expected. A glowing orange ring, with a dark central shadow. Almost exactly the size that Einstein's general relativity, combined with the previously measured mass of the black hole, predicted. The image confirmed what decades of indirect evidence had implied. Sagittarius A is, beyond reasonable doubt, a supermassive black hole. Its silhouette matches the predictions of Einstein's theory. Its size is consistent with its measured mass. The general framework astronomers had been using to describe this object was correct in the most fundamental sense. That was the triumph. But here is the thing that did not get covered as carefully in the popular press. The 2022 image was not a final answer. It was an opening question, because the image, by necessity, was an average. It represented what Sagittarius A typically looked like during the 2017 observation campaign. The actual source had been varying throughout. The brightness around the ring had been changing. Bright spots had appeared and disappeared. The image we see is, in a real sense, a stable picture extracted from an unstable source. What the image left open were the details. What was driving the variability? What was the role of the magnetic fields? Was there a jet, like the famous one extending from M87*? What was the small-scale structure of the accretion flow really like? The 2022 image was a triumph. It was also, in a way that did not become clear until 2 years later, only the beginning. In March of 2024, the Event Horizon Telescope collaboration released a new image of Sagittarius A. It was the same data, in one sense. The 2017 observation campaign, the same nights of observation, the same telescopes, the same source, but it was a fundamentally different kind of image. It was Sagittarius A in polarized light. To understand what that means, you have to know what polarization measures. Light, in physics, is a wave. Waves have an orientation. They oscillate in particular directions. When you look at ordinary, everyday light, the directions are random. You see waves oscillating every which way, all mixed together. That is unpolarized light. When light is polarized, it means the waves have been organized. They are oscillating in particular preferred directions, rather than randomly. And, in astronomy, the most common cause of polarization in the kinds of environments we care about, like the regions around black holes, is magnetic fields. When charged particles move through a magnetic field, they radiate light in particular directions. The pattern of polarization in that light traces, with extraordinary precision, the structure of the magnetic field that produced it. So, a polarized image of Sagittarius A is not just another picture of the black hole. It is, effectively, a map of the magnetic fields in the immediate environment around the event horizon. When the image was released, what it showed was striking. Strong, organized, spiraling magnetic field lines, wrapping around the black hole's silhouette in a coherent pattern, not random, not chaotic, not the messy tangle that some theories had predicted, a clean, structured, spiral pattern. The implication was significant. It told astronomers that the magnetic fields around Sagittarius A are dynamically important, meaning they are strong enough and organized enough to actively shape what the matter around the black hole is doing. They are not passive features. They are players in the dynamics of the system. And then there was the comparison. The polarized image of Sagittarius A turned out to be strikingly similar to the polarized image of M87* that had been released earlier. Same kind of structured spiraling pattern, same general orientation, same evidence of magnetic fields strong enough to matter. This similarity carried a hidden weight, because M87* has a famous, visible jet, a high-energy stream of particles shooting out from the black hole's environment, extending across thousands of light-years, glowing brightly in radio wavelengths. The polarization structure around M87** in the EHT data is consistent with what theory predicts when you have a black hole that is actively launching a jet. If Sagittarius A has the same kind of polarization structure as M87**, then Sagittarius A may have a jet too. A jet that we have not yet directly detected. This was, immediately, one of the most discussed implications in the technical literature. Some researchers argued that the polarization data clearly implied a hidden jet, and that the lack of direct detection was simply a matter of viewing angle. We may be looking at Sagittarius A nearly along the axis of its jet, which would make the jet very difficult to see directly. In effect, we might be staring straight down the barrel, and the geometry would hide the structure that would otherwise be obvious. Others were more cautious. They pointed out that the polarization pattern, while consistent with a jet model, does not require one. There are alternative explanations, purely accretion flow magnetic fields without a launched jet, that fit the data nearly as well. Until direct evidence of a jet is found, the question remains open, but the question had been raised, formally, in the technical literature. The closest supermassive black hole to Earth might have a feature we had assumed it lacked, and, if it does, the implications for understanding the energy output of low-luminosity black holes are significant. There was also a broader pattern emerging from EHT polarization studies. M87**, with a confirmed jet, showed organized magnetic fields, and now, Sagittarius A, supposedly quiet, supposedly low energy, was also showing the same kind of organized field structure. The general principle beginning to emerge. Organized, dynamically significant magnetic fields appear to be a common feature of supermassive black holes. Whether or not a jet is launched, the fields seem to be there, structured, doing work. This was a quiet but important shift in the field. For decades, simpler theories of supermassive black hole accretion had treated magnetic fields as a complication. A feature you sometimes had to include in your simulations, but not necessarily a defining property of the system. The 2024 polarization work pointed toward a different picture. Magnetic fields were not a complication, they were central. They were doing significant work in shaping how matter behaved near the event horizon, and that raised a question. If magnetic fields were this important to the structure around Sagittarius A, what else had we been missing? What would happen if we pointed a different kind of instrument at the same target, an instrument that could watch it not just for hours, but for sustained windows of observation across an entire year? Because that observation campaign was, at that very moment, already underway. In February of 2025, a paper appeared in the astrophysical journal Letters. The lead author was Farhad Yusef-Zadeh, an astronomer at Northwestern University. The paper was titled, in the careful technical language of academic publishing, Non-Stop Variability of SGR A using JWST at 2, 1 and 4, 8 micron wavelengths, evidence for distinct populations of faint and bright variable emission. Asterisk, the title alone tells you most of what you need to know. Non-stop variability. The black hole was never quiet. In any of the observation windows, distinct populations of faint and bright variable emission. There were not just one kind of brightness changes happening. There were two, qualitatively different, populations of variability. The campaign had used the James Webb Space Telescope's NIR-CAM instrument, observing simultaneously at two different infrared wavelengths, 2, 1 microns and 4, 8 microns. The total observing time was 48 hours, divided into 7 separate windows of 8 to 10 hours each, spread across an entire year, in 23 and 24. Each window was a long, continuous look at Sagittarius A. long enough to catch flares as they happened, long enough to characterize the baseline activity, long enough that if the source had been steady at any point, the observation would have caught it. It never was. The findings, as stated in the paper, were these. First, Sagittarius A never reached a steady state during any observation. Across all 7 windows, distributed across an entire year, the black hole was always varying. There was no calm baseline to which it returned. Second, 2 distinct populations of variability were detected. There were short, faint flickers, pulses lasting seconds to minutes, of relatively low brightness, and there were bright, sustained flares, events lasting hours, sometimes longer, with significantly higher brightness peaks. The 2 populations did not look like the same physical process. They appeared to be different kinds of events, possibly arising from different mechanisms. Third, the 2, 1 and 4, 8 micron observations sometimes showed correlated variability, flares appearing simultaneously at both wavelengths, and sometimes did not. Some flares were strongly chromatic, meaning they showed different brightnesses at different wavelengths. This suggested that the underlying physics was not a single process, but multiple processes operating in the same region. Fourth, the team detected approximately 5 to 6 major flare events per day. This is a significantly higher rate than prior observations had suggested. Earlier studies, using ground-based telescopes with shorter observation windows, had reported flares occurring on the order of once every several days. The JWST data suggested those earlier studies had simply not been watching long enough. The flares had been there. We just had not been able to detect them all. And fifth, the line that captured the full implication, in Yusef-Zadeh's own words, we saw something different each time. Nothing ever stayed the same. The interpretation, as the paper laid it out, was that the accretion flow around Sagittarius A is far more turbulent and dynamic than steady-state models had assumed. The 2 populations of flares may correspond to fundamentally different physical processes. One, possibly, related to magnetic reconnection events near the black hole, where twisted magnetic field lines snap and release energy quickly. The other, possibly, related to larger-scale instabilities in the accretion flow itself, where disruptions in the flow produce more sustained brightening events. But, beyond any specific interpretation, the paper made a broader point. The simple analytical models that the field had been using for years to describe Sagittarius A could not reproduce the observed variability. They were not subtly off. They were fundamentally inadequate. This finding was not reported in the popular press in any sustained way. The original 2025 paper got coverage in specialist outlets, Sky at Night, Sci News, NASA-owned communication channels, but mainstream science journalism largely missed it. The field itself, however, had been talking about these findings from the moment the paper appeared. The question that hung over the entire result was the broader one. Is Sagittarius A unusual? Or have we just never had the instruments to watch other low-luminosity, supermassive black holes carefully enough to see that they too are non-stop variable? In the months after the paper's release, several research groups began reanalyzing archival data of other supermassive black holes, looking for similar variability patterns at sufficient time resolution. The results are preliminary but suggestive. Some other low-luminosity AGN, when observed carefully, also seem to show more variability than steady-state models predict. Sagittarius A may not be alone. It may simply be the first one we have been able to watch closely. If that holds up, then our entire framework for thinking about supermassive black holes in low-luminosity galaxies, which describes most of the supermassive black holes in the universe, may need to be reconsidered. There are 3 serious ways to interpret what Sagittarius A is doing. They sit on a ladder, conservative at the bottom, bold at the top. Each one explains some of the data. None of them captures the full picture by itself. And together, they outline the question that the JWST observations have forced the field to confront. The conservative interpretation is that Sagittarius A is unusual among its kind. In this view, our supermassive black hole may simply be an outlier. Most low-luminosity supermassive black holes, the argument goes, really are quieter. Sagittarius A happens to be unusually active for its category for reasons specific to its particular environment. The conditions at the galactic center, recent gas inflow, particular magnetic field configurations, or other local factors that make it more energetic than the typical black hole of its mass and luminosity class. The supporting evidence for this view comes from comparisons with other supermassive black holes in similar mass ranges and luminosity classes. On average, those other black holes do show less variability when observed. SGR A really is more active than most of its peers, by every measurement we have. The weakness of this view, however, is the one we just identified. Most other low-luminosity, supermassive black holes have not been observed at the level of detail. JWST has now provided for Sagittarius A. The apparent contrast may reflect observational limitations. We have not watched long enough, with sensitive enough instruments, to detect the same kind of variability elsewhere. This is still the most common view in the scientific community. It is, however, holding less confidence than it did a few years ago. The 2025 JWST paper has made many researchers reevaluate. The moderate interpretation, which has been gaining ground, is that our models of low-luminosity black holes need updating. In this view, Sagittarius A is showing us that low-luminosity supermassive black holes are not as quiet as the textbooks suggested. The category itself needs revision. Other supermassive black holes in similar conditions are probably also more active than current models account for. But we have not been able to observe them as carefully as JWST has now observed SGR-A. With better instruments and longer observation campaigns, we would expect to see similar, non-stop variability across the population. The supporting evidence for this view is the early hints from reanalyses of archival data on other AGN. Those data, examined with attention to high-time resolution variability, are beginning to show patterns that look more like Sagittarius A than like the textbook quiet baseline. The weakness is that this view requires accepting that decades of analytical models have systematically underestimated black hole activity. That is a significant claim, and it makes some researchers cautious. This view is gaining ground, especially among those involved in interpreting the JWST data and in modeling supermassive black hole accretion at high time resolution. The bold interpretation is that our framework for accretion physics may need fundamental revision. In this view, the patterns observed at Sagittarius A, multi-wavelength correlations that don't fit simple models, distinct variability populations suggesting multiple physical processes, the failure of analytical models to predict the data, may indicate something deeper. The basic physics of how matter accretes onto black holes may be more complex than current models capture. Magnetic reconnection, plasma turbulence, and dynamical effects may play larger roles than previously assumed. And the interactions of these processes may produce emergent behavior that simple models cannot reproduce. The supporting evidence comes from numerical simulations, general relativistic magnetohydrodynamic simulations, known in the field as GRMHD, when run with sufficient resolution and physical realism, have begun to reproduce some of the variability features observed at Sagittarius A. This suggests the physics is, in principle, understandable, but it requires more sophisticated treatments than the simple analytical models that have been used historically. The weakness is that this view requires substantial revisions to analytical frameworks, teaching materials, and the tools astrophysicists use to interpret black hole data across the field. This is a respected minority view, particularly among GRMHD modelers, the researchers building the most physically realistic simulations of black hole environments. It is worth pausing here for an important note. None of these three interpretations involves anything mystical or beyond established physics. The bold interpretation just says we need better physics within the existing framework, not different physics. There are no aliens. There are no exotic objects. There is just a roughly 4 million solar mass object at the center of our galaxy doing physics that is more complex than we previously had the tools to describe. And here, before we leave the theoretical landscape and return to the data, there is something worth saying about why this story matters at all. Why are humans so drawn to the centers of things? Not just literal centers, not just galactic cores, but the centers of any system we encounter, the middle of the maze, the heart of the question, the place where everything else points. Sagittarius A sits at the gravitational center of the Milky Way. Every star in our galaxy, including our Sun, is, in a sense, orbiting around it, the center of our cosmic home. And for most of human history, we did not even know it existed. We could not see through the dust. We had no tools to detect the radio source. Sagittarius A was simply there, doing whatever it was doing, completely hidden from human awareness. For most of human history, the universe was a still photograph. Stars were dots on a sky. Galaxies were faint smudges. The universe presented itself as something static, a frozen image that could be studied, but not, in any real sense, watched. Now, for the first time, we are starting to see it as a movie. What the movie shows us, even at the very center of our own galaxy, is that nothing is as quiet as we thought it was. After everything we have seen, the discovery in 1974, the orbital tracking that confirmed the black hole's existence, the 2022 EHT image, the 2024 polarization revelation, the unprecedented JWST observations of 2025, the three competing interpretations. The question is no longer whether Sagittarius A is doing something unusual. It is. The question is what that unusual behavior means for everything else we thought we understood about black holes. And here is where the story takes a turn that most coverage of this topic has never gotten to. Remember what we asked at the start of this video. What is actually happening at the center of our galaxy? Why does Sagittarius A never stop flaring when every theory said it should be quiet? Why are the magnetic fields around it organized into a spiraling structure that may be hiding a jet we have never directly detected? After tracing this story from the 1974 discovery, through the orbital tracking work of Genzel and Ghez, through the 2022 EHT image, through the 2024 polarization revelation, through the 2025 JWST observations that overturned the analytical models, through the three competing interpretations, here is what we now know. And, just as importantly, here is what we still do not. We know Sagittarius A exists. We know it is approximately 4 million times the mass of the Sun. We know it is consistent, to high precision, with the predictions of Einstein's general relativity. We know it has organized, spiraling magnetic fields, confirmed by the 2024 EHT polarization image. We know it shows continuous flaring activity at unprecedented levels, confirmed by the 2025 JWST campaign. We are still debating whether this activity is unusual to Sagittarius A or representative of similar black holes throughout the universe. We do not yet know whether it has a hidden jet. We do not yet know what specific physical processes produce the two distinct populations of variability, JWST, detected. And we do not yet know whether our analytical models of black hole accretion need fundamental revision. That is where the science currently sits, and that is where most public coverage stops. But the technical literature does not stop there. Here is the strange thing about how Sagittarius A has been covered in popular media. The story tends to come out in two forms. The first form is the celebratory version. Astronomers image the black hole at the center of our galaxy, iconic photograph, triumph of modern astronomy. That version focused almost entirely on the 2022 EHT image, treats the photograph as the conclusion of the Sagittarius A story rather than its beginning. It implies that we now know what this black hole is, and the science around it has been settled. The second form is the alarmist version, black hole going active, could it threaten Earth? Mysterious activity at the galactic center. That version exaggerates the actual findings into something that sounds like impending danger, when the real situation is nothing of the kind. Sagittarius A is 26,000 light-years away. Its activity, however unprecedented, poses no threat to anything in our solar system. The framing of cosmic threat is, plainly, false. Both versions miss what the technical literature actually says. Let me give you specific examples. The 2022 EHT image was, by any measure, a triumph. Nobody disputes that. But the way it was covered, as the answer to what Sagittarius A is, was misleading. The image confirmed the silhouette. It did not resolve the questions about variability, magnetic fields, jets, or the underlying accretion physics. Those questions remained open after the image was released. The popular framing, in many cases, suggested otherwise. A second example. The 2024 polarization image and its implications for a hidden jet received vastly less coverage than it deserved. Major newspapers and general audience science publications either ignored the result or covered it briefly without explaining its significance. Yet, within the field, the polarization paper was one of the most discussed results of 2024. Precisely because it raised the jet question that had been quietly hanging over Sagittarius A for years. A third example, and this one is the most striking. The Yusef-Zadeh JWST observations, published in February of 2025, are arguably the most scientifically interesting findings in galactic center astronomy in the last decade. They directly challenge the analytical models that have been used for decades. They suggest that our entire framework for understanding low luminosity, supermassive black holes may need updating. And yet, they have been almost absent from mainstream science journalism. Specialist outlets have covered them appropriately, but the major newspapers, the general audience science publications, the broadcast science segments, most of them simply did not cover this story. This is a pattern in science journalism that researchers themselves complain about. The exciting visual finding gets sustained coverage. The more nuanced, more technically significant follow-up findings get buried, even though they may matter more for our understanding of the universe. A fourth example. The internal scientific debate about whether analytical models of supermassive black hole accretion need to be substantially revised has been happening in journals, at conferences, and in the day-to-day conversations of the field. Researchers are openly discussing whether decades of work needs to be reconsidered. This is a significant moment in the discipline, but it is rarely presented to general audiences because it does not lend itself to a simple headline. There is also a quieter point that deserves attention. The framing of Sagittarius A as settled after the 2022 image has actively impeded public understanding of how much remains genuinely open. People who saw that image and who were told it was the answer to what the black hole at the center of our galaxy is, naturally moved on. They assumed the story was complete. They missed the next chapters as they were being written. the technical literature has been telling a different story all along. The 2022 image opened a door. The 2024 polarization image walked through that door into a room with new questions. The 2025 JWST observations made it clear that those questions are not just academic, they are forcing the field to reconsider its foundations. That is what the headlines missed. Not a hidden truth, not a cover-up. Just the more complete picture that the technical literature has been quietly assembling for years, while the public conversation moved on under the impression that the story was over. In the months and years since the 2025 JWST paper, the picture has continued to develop. New data has been coming in. New analyses have been published. The story is, in the most literal sense, still being written. The first major development has been continued multi-wavelength monitoring of Sagittarius A. Several instruments have been observing the black hole continuously. The Chandra X-ray Observatory and New Star, both space-based X-ray telescopes, have been recording flare events. JWST has been continuing infrared observations beyond the original campaign. The Atacama Large Millimeter Array, ALMA, in Chile, has been observing in submillimeter wavelengths, and ground-based near-infrared telescopes have been contributing complementary data. The result is a multi-wavelength dataset of unprecedented breadth. Recent papers have begun describing flare events with detail that earlier observations could not capture. Some of these events show sequences of brightness increases across very different wavelengths, submillimeter, X-ray, near-infrared, all happening within roughly an hour of each other. This kind of multi-wavelength correlation is, in some cases, exactly what theoretical models predict. If a single physical event is heating different populations of particles to different temperatures simultaneously, in other cases, the correlations don't quite match any standard prediction. The data, in other words, is genuinely puzzling. Some of it fits theoretical models, some of it does not. And the difference between the two is teaching the field where its current models work and where they break down. The second major development is in observation strategy. Yusef-Zadeh's team, having published the initial results, has been advocating for a much longer continuous JWST observation of Sagittarius A. Their proposal is to observe the black hole for 24 uninterrupted hours in a single window. The reasoning, in his own words, is that competing with noise becomes much easier when you have more time. Faint signals that were lost in the noise during shorter observations might be visible in a longer continuous look. And the longer window would also allow tests of whether the flares show any periodicity, whether they repeat themselves on a regular schedule, or whether they are truly random. This is the kind of question that simply cannot be answered with shorter observations. Whether the flaring is random or quasi-periodic has direct implications for what physical mechanism is producing it. A periodic signal would suggest an orbiting structure or a regular oscillation. Truly, random flaring suggests a more turbulent process. The 24-hour observation, if it happens, will be a major test. The third major development is in instrumentation. The Event Horizon Telescope is preparing for its next-generation upgrade. The current EHT array is being expanded with additional telescopes, larger bandwidth, and new observing frequencies. The planned next-generation EHT, sometimes referred to as NG-EHT, would dramatically improve imaging capabilities, potentially enabling not just static images of Sagittarius A but actual movies, with time-resolved frames showing the accretion flow as it changes from minute to minute. These developments are not science fiction, they are in active planning. What this means is that the story of Sagittarius A is not closing, it is opening wider. Every generation of instruments has revealed new behavior at the center of our galaxy. The next generation will reveal more, and here is what makes all of this truly remarkable. We have spent decades describing supermassive black holes as monumental objects, features of the universe that just are static, permanent, defined by their mass and their event horizons, and very little else. But what Sagittarius A has been telling us in the last few years is something different. Black holes are not monuments. They are environments. They are places where physics is happening, magnetic fields are reconnecting, plasma is heating and cooling, jets may be forming and dissipating, accretion flows are turbulent and unsteady. They are, in every way that matters, active, not in the sense of being dangerous, in the sense of being alive, in the way that any complex physical system is alive, full of motion, change, structure, and surprise. And the closest one to Earth, the one we can finally watch in real time, is showing us that the simple picture we built of these objects was incomplete. Not wrong. Incomplete. The shadow at the center of our galaxy is real. The mass is real. The general relativistic predictions about what its silhouette should look like, those have been confirmed. The framework Einstein built more than a century ago describes Sagittarius A with extraordinary precision. But what is happening around the shadow is more dynamic, more complex, and more interesting than anyone fully predicted. The accretion flow is not steady. The magnetic fields are dynamically important. The variability does not pause. The physics, when looked at with sufficient resolution, refuses to settle. Let that sit for a moment. The closest, supermassive black hole to Earth is not quietly sitting at the center of our galaxy. It is alive, in every meaningful sense, bubbling, flaring, restructuring, possibly launching invisible jets we have not yet detected. It has been doing this the whole time we have known about it. We just couldn't watch closely enough to see it. And the question is no longer what is Sagittarius A. The question is what every other supermassive black hole in the universe is doing, that we have not yet had the instruments to observe. The question is whether the universe, at its centers, is far more dynamic than we thought. Whether the engines that shape galaxies are more energetic, more variable, more active than the textbooks describe. The answer, increasingly, looks like yes. And the most remarkable thing is that we are finding this out, in real time, at the closest possible vantage point, 26,000 light-years from a process that has been hidden in plain sight for as long as humans have looked up at the sky and wondered what was at the center of it all. But there is one more piece to this puzzle. Because Sagittarius A is, in the end, a relatively small supermassive black hole, there are others, much larger, much more active, and far more violent, at the centers of other galaxies. And one of them, in a galaxy not too far from our own in cosmic terms, has been doing something even stranger than what Sagittarius A has been doing. Something that, if confirmed by the next generation of observations, could change our understanding of what supermassive black holes are capable of, in ways that make even the JWST findings look almost ordinary. That is a story for next time. Tonight, we did not just learn about a black hole. We watched what happens when a roughly 4 million solar mass object at the center of our galaxy, an object we thought we understood well enough to put on textbook diagrams, started telling us, through the most powerful telescope ever built, that the diagrams were missing something. We saw a small radio source noticed in February of 1974 by 2 American astronomers working with an interferometer in Green Bank, West Virginia. They called it Sagittarius A. They didn't know, at the time, what they had found. They were so cautious about the implications that they never even wrote the words black hole in their paper. We watched 2 teams on opposite sides of the world spend decades tracking individual stars on tight orbits around an invisible point. Their work, ultimately, won them a Nobel Prize. It also confirmed, beyond reasonable doubt, that there was a supermassive black hole at the center of our galaxy. We watched a global telescope array spend years building the technology to image its silhouette. We watched the 2022 image become a cultural icon, displayed on screens around the world, taught in every introductory astronomy course. And then, we watched the same object, in 2024 and 2025, quietly tell us that the story was just getting started. The polarization image revealed organized magnetic fields and hinted at a hidden jet. The JWST observations broke the steady-state model entirely. Sagittarius A turned out to be far more interesting, far more dynamic, far more alive than the textbooks had been ready to describe. This was not a story about an object. This was a story about how a familiar piece of the sky, when watched closely enough, refused to stay familiar, and yet, even now, the case is far from closed. We do not know whether Sagittarius A has a hidden jet. The polarization data is suggestive. Direct evidence, one way or the other, is still missing. We do not know what specific physical mechanism produces the two distinct populations of variability that JWST detected. The leading candidates, magnetic reconnection events and larger-scale accretion instabilities, are both plausible, but neither has been confirmed in detail. We do not know whether other low-luminosity supermassive black holes are similarly active, or whether Sagittarius A is unusual. Early reanalyses of archival data are suggestive, but more careful observations of other black holes will be needed to settle the question. And we do not know, in the largest sense, whether our analytical models of black hole accretion need fundamental revision, or whether the simulations being developed will turn out to be sufficient. These questions are open. The next generation of telescopes, the expanded EHT, the proposed space-based interferometers, longer continuous JWST campaigns, will determine how many of them get answered. There are a few things worth taking from this story that go beyond Sagittarius A itself. The first is that familiarity is not understanding. We thought we knew what Sagittarius A was. We had a picture. We had textbook descriptions. We had iconic images. The 2025 JWST data showed us how much was hiding in plain sight, behind the familiarity we had developed with this object. The second is that new instruments do not just confirm old findings, they reveal what was always there, but unobservable. The flares were happening before JWST. The variability was always there. We simply could not see it. Every generation of telescopes shows us a universe slightly different from the one our predecessors thought they were studying. The third is that black holes are environments, not monuments. Physics happens around them: magnetic fields, plasma flows, turbulence, magnetic reconnection. Black holes are places where complex things occur, in motion, in time. The static picture we have carried in our heads is, in important ways, incomplete. The fourth is that the closest object to us in any category is the one we should study most carefully. Because everything we learn about it, we extrapolate to objects we cannot study as well. Sagittarius A, as the closest supermassive black hole to Earth, is doing scientific work that benefits the study of every other supermassive black hole in the observable universe. And the fifth is this. The most important scientific findings often look like small anomalies in obscure papers, until they accumulate into a pattern the field can no longer ignore. The flares at Sagittarius A were anomalies for years before the 2025 paper made them undeniable. We are living through the moment when those anomalies become the new picture. So, I want to leave you with a few questions tonight. What does it mean that the most studied black hole in the universe, the one closest to us, the one we have spent decades observing, is still surprising the people who study it for a living? What does that say about how much we actually know about black holes much further away, that we cannot watch this carefully? When we look at the activity around Sagittarius A, the constant flaring, the spiraling magnetic fields, the possible hidden jet, are we looking at something unique to this object? Or are we looking at the first clear glimpse of what is happening at the center of every galaxy in the universe? What other quiet objects are we missing, simply because we have not yet been able to watch them long enough? Sit with those for a moment. They are bigger than Sagittarius A. If this story stayed with you, tell me in the comments, which moment was the one that pulled you in? Was it the 2022 image of the orange ring, that first direct picture of our galaxy's central black hole? The 2024 polarization revelation, with its hint of a hidden jet? The 2025 JWST observations that broke the steady-state model? Or the realization at the very end that the closest supermassive black hole to Earth is alive in ways we are only just learning to see? I want to know. And if you want more deep space mysteries told this way, current science, told carefully, with the full story rather than the simplified version, subscribe to Galaxy Pulse. We go beyond the headlines every single time. I will see you in the next one. 26,000 light years from here, at the very center of the only galaxy we have ever called home, something is happening that we do not fully understand. It is happening right now. It has been happening for as long as we have been alive, for as long as humans have existed. And only in the last few years have we gathered enough light, with the right instruments, to finally start watching.